In this lesson, we're going to explore the laws of Newton and how to apply them to solve a few common questions in A levels. But be advised, we are not going to go into the details of first law, second law, and third law. We're just going to briefly discuss them because we've already done that in an O levels video for forces. So there's no point going through that again. You can watch that video for a detailed understanding of first, second, and third law. So I'm going to discuss questions with them, how to visualize those laws and how to put those laws into the question. So the first one says resist change in motion. This is basically inertia, and it actually comes from the first law, which is all about balanced forces, right? So the first law says that if an object has balanced forces, for example, the forward force, which is 100 newtons, and let's say the backward force, which is 100 newton as well, if they are equal, then the acceleration is zero and the object is considered to be in a balanced situation or equilibrium. So there are two things that the object could be doing. It could be moving at a constant speed, and it could be at rest. These are two options available or possible from the first law. The second law suggests, and in terms of inertia, inertia depends on mass, right? And it is the property to resist change. The object does not want to change its state of motion. And what are those states of motion? The first one is constant speed, the second one is at rest or being at rest. So if an object is moving, it wants to stay in motion. If it is already at rest, it wants to stay at rest. So it wants to maintain that position no matter the circumstances, and it depends on its mass. So a more massive an object is going to be, it is going to be more difficult for the object to observe a change because of a resultant force, right? So, for example, if there is a truck, we want to move a truck from its position, it is very difficult to do. And if it is already moving, then to stop the truck is also difficult. As opposed to a tennis ball or a ballpoint pen, if you want to move it, you can do that very easily because it cannot resist that change as much as a more massive object can do that. So this is basically the you can say summary of the first law is inertia. The second law suggests that the resultant force produces an acceleration. Now, students generally talk about this in terms of force producing an acceleration, but that would be wrong. The correct way to look at this is that a resultant force produces acceleration. So notice that if, for example, we have an object that is experiencing 50 newtons forward and 50 newtons backward. When we talk about these forces, we are going to label them. We will label them as force or forces. This will also be called a force. If I want to find the resultant force, then I have to be careful, and we will be subtracting this 50 from this 50, or a forward force minus the backward force. Well, 50 minus 50, the resultant is 0 newtons. So when we talk about the second law, we are actually talking about the resultant force, not just any force. The result, the combined effect of all the forces. So if I use the resultant force formula, that will be F equals to ma. That means that the resultant force, or whatever is left behind, or whatever is in surplus, whatever is left out of the applied forces, will be put here, and that will cause an acceleration in that respective mass in the same direction, right? So similarly, if we were talking about an object that had an unbalanced situation, for example, the forward force is, let's say, 100 newtons, and the backward force is, let's say, 30 newtons, then this 100 will also be referred as a force, a pulling force, and 30 newtons will be referred as a stopping force. But when we talk about the resultant force, Fr equals to ma, in Fr, you're already doing that mentally, is that you're subtracting 100 from 30 because they are in the opposite directions. So 100 minus 30 gives us 70 equals to ma. Now this 70 becomes the resultant force. This is not just a force, this will be referred as a resultant force. So second law says that there needs to be a resultant force to produce an acceleration. What it is trying to say is that there needs to be an unbalancing effect or unbalanced effect among the applied forces in order for an object to observe an acceleration or a change of motion, right? Similarly, we have momentum. I have a separate video for this, which is mass into velocity. You can check that out. Use of rate of change of momentum. We've also done that proof in that video that force is basically equal to rate of change of momentum. We've done that. The proof is also a part of your course. You should be able to derive that. And the fifth one is apply each law of Newton. We are going to do that in the questions. Then we have point number 6, the concept of gravity, gravitational field, and gravitational acceleration, which is basically W equals to mg. But before going towards that, we are going to revisit Newton's third law. Again, I have discussed all of the misconceptions in the previous O levels video as well. I will add that video's link in the description as well so that you can go check them out directly. Right. So Newton's third law suggests that the action and reaction should be equal and opposite, which is a very common knowledge and understanding. But in terms of the truth, in terms of its application, we generally sometimes get confused by that. So one thing that I would like to add in this position is that the nature of force, or the cause and effect of the forces, or you can say that the involved object in that scenario should be having those actions and reactions of forces because of the same reason. So I'll also discuss this one common example that is misconception between the students that I've also discussed in that video. So if there is a book and table example, the weight of the book is because of the Earth's gravity, but the normal reaction is because of the uh, table's atoms, right? So normal reaction is coming due to the intramolecular forces of the table, and the weight is because of the Earth's pull and gravity. Although the book is stationary, which says, or which tells us that both forces are equal and opposite, which is acceptable, but they are not Newton's third law. The action and reaction pair do not fall in this category, because if we look closely, this weight is being caused by the Earth, but the book was also pulling the Earth towards itself. So if the Earth has applied an action force to create this weight, then the book has provided a reaction force to generate the same weight by pulling the Earth towards itself. These two forces will qualify for the Newton's third law, but this one, normal reaction, will not. So generally, what it comes down to is that whenever weight is involved, whenever the pull of any planet's gravity is involved, we will not be making it, or we will not be considering it as a third law pair with any other force other than the planet's attraction, or other than the object's attraction towards that planet. Okay, and one of them is actually from Newton's law of gravity, that all massive objects are attracting each other. So let's say if we talk about the sun, we talk about the earth, and we talk about the moon. This is a very common question in terms of P1 MCQs. He mentions a few forces. Now we're going to discuss them. So if the earth is being attracted by the sun, let's call this force P, then the sun is also being attracted by the earth, which is, let's say, force Q, although they are related by the gravitational attraction. The moon is attracted by the earth, and the earth is also being attracted by the moon. So let's call them R and S. And the moon is also being attracted by the sun, and the sun is also attracting the moon as well. Or the sun is being attracted by the moon as well. So let's call them T and W, right? So he will mention, or he will label these forces, but not name them exactly. He will label them as A, B, C, D, or W, R, X, T, or something like that, what we've just discovered on the screen. And he will ask you to identify the pairs of the Newton's third law forces. So any pair goes as long as the involved objects are similar. You cannot say that W will make a third law pair with P. Why? Because W is the moon's attraction on the sun, while as the P is the sun's attraction on Earth, right? But if they were opposite pairs, then that would again qualify for the Newton's third law. And last but not the least, we are supposed to understand W equals to mg, and we have done this extensively in O levels. What is the meaning of this formula, right? And we have also have a video, or also have a lesson for A2 gravitational field, in which we have discussed this formula in detail, where it actually comes from and what it actually means. But in AS or in O levels, we are just required to solve questions of weight using this formula, right? Okay, let's move on towards the application of this idea, or application of these laws. So in the first question, it says a tractor has a mass of this. Okay, so we have a tractor which is being pulled by, or which is connected by a tow bar to a trailer which is at the back, right? So this is the trailer, which also has a mass of 1000 kg. So this is 1000 kg, and this is also 1000 kg. So the total mass of the system comes down to 2000 kgs. Now let's see. The total resistance of the motion of the vehicle is 4000. Now when he says this, it means that if you lump them together, if you combine both of them together as a single object, then they are experiencing 4000 newtons of back uh, resistance force, right? Now then he tells us that the quarter of this resistance is acting on the trailer. So If this is 4,000, a quarter of that would be divided by 4, which gives us 1,000. So the trailer is experiencing 1,000 newtons of drag, and the truck or the tractor is experiencing 3,000 newtons of drag. But if you lump them together as a single object of 2,000 kg by adding these two masses together, then that will become 4,000 on an average on a whole object. Now he tells us that the tractor is moving along horizontal with a constant speed. Now this is the next key point that you should keep in mind. If it is moving at a constant speed, then the acceleration is equal to 0. It means that there is no resultant force. The resultant force is 0, which means that if I know about the resistance force, for example, if I know that an object is experiencing 4,000 newtons of drag, friction, air resistance, then most definitely the force provided by the engine is exactly the same. It's also 4,000. So that pulling force minus the stopping force ultimately gives me a 0 answer, leading to 0 acceleration. So always keep an eye for this idea. Constant speed means that all the forces are balanced. So what is the force exerted on the tractor by the tow car? So now we want to understand that this trailer is exerting a force on the tractor, right? This is happening through the rod, through the chain, through the tow bar that is connected between the objects. And we know that rods, chains, tow bars, threads, they experience a force of tension, or they reflect one object's force to the other one through the force of tension. Now this 1,000 newtons of drag will be experienced by this tractor, will be observed or will be felt by this tractor through this tow bar, and that will be in the backwards direction as 1,000 newtons of force, right? So the tow bar basically is just telling this tractor or representing this drag force on the tractor by a force of 1,000 in the backwards direction, right? So this value will be actually 1,000. So the tow bar is experiencing a force of 1,000 newtons, or is providing a force of 1,000 newtons for this trailer to move. Now, if we just isolate the trailer, we see one thing, that the trailer is observing 1,000 newtons of drag force, which through this tow bar are being represented in the backwards direction exactly the way this is. Now, if the whole system is moving at a constant speed, that means there should be a forward force of 1,000 newtons coming from somewhere, 1,000 newtons of force, right, in the forward direction. And we know that tension is basically going to be in both directions, but we need to find out their representatives. Now, where is this 1,000 newton coming from? So 1,000 newtons of force will be coming from the tractor's engine, which in turn is actually applying a force of 4,000. But how is it doing that? So 1,000 newtons is needed to balance, or is needed to make sure that the trailer moves at a constant speed with 0 acceleration. And 3,000 newtons of that force from the engine is being utilized to counteract its own 3,000 newtons of friction. Collectively, the engine has to provide a force of 4,000 newtons, out of which 1,000 is being provided to the tow bar so that the trailer can be pulled along successfully, and the 3,000 of that is used to cover its own resistance, its own friction. So 1,000 will be the final answer. This is again an application of Newton's third law. It's actually coming or represented or representing in terms of the tension aspect, right? Okay, the next question actually utilizes third law again in terms of solar systems that I just discussed with you, right? So it tells me that a book rests on the table, and if the weight, he tells you the first condition himself. If the weight of the book is the action force, for example, if this weight is the action, then where's the reaction? So we know that from third law, it should be the pull of the book on the earth. The book is pulling the earth towards itself. So the pull, not the push. We eliminate option C and D. The pull of the book on the earth, which will be in the upwards direction. So option A will be the closest possible answer to this option, right? One more thing that we need to understand at this point is that we must understand that normal reaction will be exerted. It is present, but it does not fall in the category of Newton's third law. Okay. All right. So next question is about second law. We're going to discuss multiple options. Now, first of all, it tells me that it is moving at a terminal velocity. If it is moving at a terminal velocity, that means the acceleration is 0. That means that the resultant forces are 0. That means that the upward forces, all the upward forces and the downward forces are basically equal. How do we justify that? So from the resultant force, we have F equals to ma. the downward force minus the upward force equals to ma. Now, if I know that the acceleration is 0, this whole side becomes 0. So I'm left with an equation that down, up, minus up is equal to 0. If I bring up on this side, this becomes the downward force being equal to the upward forces, right? So in this situation, or in this scenario, the weight is in the downward direction and the drag and the upthrust in the opposite direction. So simply put, if the resultant or if the acceleration is 0 because of the terminal velocity, I can say that the weight, the downward forces, or all the downward forces are basically equal to the upthrust plus the drag of the system. They're supposed to be equal. Now, you will not find an equation in this option or in these options. So what he has done is to trick you and rearranged this equation by bringing up thrust to this side. So this becomes W minus up thrust is equal to D, which now is very close to the option C. Okay. Now, one thing to be noticed is if the drag is in the upward direction, it is very likely that the motion of the object is downwards because we know that drag and friction are the motion, you can say they oppose motion in every circumstance. So if the drag is upwards, most definitely 100% the object is moving downwards. If this object was moving upwards, be advised, if this was moving upwards, right, then the upthrust generally, upthrust is always in the upwards direction, right? But this time the drag will be downwards and the weight will still be downwards. In this case, the situation or the equation will become, if it is in terminal velocity, that the upthrust is equal to W plus D. We just combine these two forces and equate it to this one, right? So keep an eye on this system, or in this situation, it is he's going to change this. Now, for example, if this was not constant speed and it was accelerating in any direction. If it was accelerating upwards or it was accelerating downwards, then we would have involved this greater than or less than sign. Whichever side would have been greater, that would have been put in the equation. So let's say if it was moving downwards and it is accelerating, that is most definitely weight is greater than drag plus upthrust, right? So again, this is an application of Newton's second law, okay? But of course, summarized or you can say concluded at first law, terminal velocity, constant speed, no resultant force, balanced forces. This is first law. Okay. Now, this is a common question in terms of second law again. There are multiple ways to solve this, but we are just going to go towards a very simple and straightforward shortcut. You will see this question in mathematics, A levels mechanics as well. So you have to make an equation in that paper with reference to T, but we are not going to get into that. We're going to make it much simpler. So since he says that this is a rough surface, I'm sure that he's going to give me friction for the surface, which he does, mentioning 6 newtons. So this box is in contact with the surface. So backwards, it will actually be 6 newtons of force trying to resist the motion of this object. Now we know that if we allow this, if this system to move, then this box will move downwards and this box will slide to this side. I will show an animation for this as well to make it easy to understand. So I understand that there is one pulling force and there is one stopping force. He's asking me to find out the acceleration. So how do we do that? We do that by using the Newton's second law, which is Fr is equal to ma. Fr, resultant force. This says F equals to ma, but I like to write down R in this situation so that we remember this is not just one force, this is multiple of forces. So the pulling force is actually the weight of this object, which will be mg. And the stopping force of the whole system is only the friction experienced by this block. So what I'm going to do, I'm going to write down this equation, mg minus F. This mg is the weight of this 2 kg block. This F represents the friction that is represented and equals to ma. Now, one more thing over here. What will be the mass that is going to be put in this equation? Basically, this resultant force, or whatever we are going to be left with, is responsible for moving not only this block, but also this block, right? So this is going to become 8 plus 2. So what we are going to write down over here is 2 into 9.81, because this is mg, so 2 multiplied by 9.8 minus 6 equals to the mass of the whole system, all the connected bodies, is 2 plus 8. I'm writing this separately so that we'd understand what we've done. Otherwise, I could have written down 10 as well. Now, if you find that acceleration, this was going to be 1 point, in some decimal, I think, 1.36. Yes. So this becomes 1.36 meters per second square, but we know in A levels we have answers in two significant figures. This will be option A. Now, let me show you an animation for this. You can see the system right in front of you in this situation, but let's see how it moves. Okay. Let's allow this. Now you can see that M1 is moving down and M2 is being slid along the surface, right? So this is how the system is actually moving. That's why we have done it this way. Okay. Let's try to observe this from another perspective. We are going to encounter that question just now. But before we go towards that, we're going to see that visualization as well, right? So if we change the angle a bit, let's say in this situation, then it becomes something else, right? In this situation, what's going to happen is we'll have to make components, right? So how to make those components? So what we do is we actually take this as our horizontal system, right? One of the angles, the weight of the object is actually going to be downwards because of the Earth's gravity. One of the components is going to be in this direction, right? And one of the components is going to be in this direction, right? So out of these two components, which one will be responsible for pulling it downwards? So since this component is mg because of the Earth's gravity, and the angle which is 40.3, whatever angle this angle will exactly be the same, and this is simply through the geometry of triangle, right? So this is, let's say, 40.3. Now, we know from vector components equation that this side will become mg cos of 40.3, and this will become mg sine of 40.3. Okay, and if you observe this component, which is the mg sine theta, basically this component, if drawn at this point, is actually replaced at this point, which is going to be now responsible for pulling this object downward. So this will be mg sine 40.3. So if I had to make an equation for this system, how would that be? This is the m1g, the pulling force of this mass, and this is m2g, the pulling force of the other mass. And one more thing, what is this mg cos theta good for? Basically, this is actually the representative of the normal reaction. So this normal reaction will be m2g cos of theta, which is 40.3, right? So if I had to make the equation for this system, how would that go? That would be the resultant force equals to ma. The resultant force, one of them is this one, and one of them is m2g sine theta. So that would be m1g minus m2g sine theta equals the mass of both systems, which is m1 plus m2 into acceleration, right? So, and of course, we don't know yet whether this one is greater than this one or whether this one is greater. We don't know that. We can calculate it and we can understand which one is going to pull the other object. If this mg sine theta is greater, then of course this system will slide downwards. If m1g is greater than the other one, then the system is going to be pulled along like this under these circumstances. Now, let's clear the screen out and see how the system is actually going to behave, right? Okay. Let's play this video and see what happens. As you can see that it is sliding downwards, which means that m2 sine theta component would have been greater than m1. This is a common example in P1 MCQs as well. We will see that later. And if we go to the reset position and go to this situation, this is also one of the common situations in A levels as well, that we have a pulley question in which two objects are connected in this way. In this system, the relative angles are eliminated and we just go back to the angles. Now we see that this is m2g and this is m1g. So simply put, this equation for acceleration would be m1g minus m2g equals to m1 plus m2 into acceleration, right? There will be no angle involved because one of them is not on the slope. Okay, all right. Let's play this out. And we can see that m2 is a bit greater than m1, so we expect m1 to go downwards. If we increase m1 to be on very large size, then you will see that this will start coming down and m2 will start going upwards. So I hope that we understand how this visualization actually works. Okay, let's move on to the question. Okay, so this is that question that I just showed you the animation of, right? So he's asking us that mass m moves down the slope and which expression should be correct. Now we understand that to make components, this will be the component of weight, which is mg, and this will be the component of the normal reaction, and this will be the component of the pulling force responsible for pulling it down. And we know that this theta is actually the same angle theta given over here. So the angle in front of theta is the sine function, so this becomes mg sine theta. So I can just straight away cancel the cos answers of the system because this is not going to be my answer, or this is not eventually going to be my answer. Now, if this system is moving downwards or is accelerating downwards, that means that this mg sine theta force must be greater than this mg force, which is mg, right? For in order for this to be accelerating or in order for this to be moving, eventually start moving, right? So it says that it is held stationary, but it starts moving. That means one of the forces is greater than the other. So G cancels out from both sides, and I apologize, this one M should be larger. This one should be mg sine theta, capital M, right? So G cancels out, so we are left with the m sine theta greater than small m. So replacing this equation, taking m to the other side, we are left with m sine theta greater than small m divided by capital M. And the one answer that actually matches this description is this option C. Okay, let's go back to the other questions that we have. Now, you will also encounter questions of this level, which are not directly taught in the classroom, but we expect you to understand how to solve them. Now, let's see how to solve them and what the examiner is expecting. First of all, you need to keep in mind the topic of homogeneity. Now, what is homogeneity? Homogeneity suggests that the equation on the left-hand side is equal to the equation on the right-hand side. In terms of units, units should be same on both sides. Now, we're going to keep this idea in mind and try to make sure that we can find out Newton somehow in our formulas or in our manipulation of formulas. We're going to find Newtons. We're trying to find out force one way or the other. Now, it tells me that there is a speed of wind speed is 33 meters per second, and it reduces to zero when it hits the wall. The area of wall is given to you. The density of air is given to you. He wants you to find out what is the approximate force exerted on the wall due to air. You can see that this question is taken from May-June 2013, paper variant 1-2. Okay, so let's visualize what's happening with the wall. So this is the wall, for example, and it is experiencing an air with a speed of 33 meters per second. Now notice this 33 meters in 1 second. It means that in 1 second, if I allow this air to move, it would have moved one in 1 second, it would have moved a distance of 33 meters if I had allowed it to move, right? So this will be used to find out the volume of air that is actually experienced by this surface of wall. Now, since I'm trying to find out the force, the first thing, and I have velocity, I have some volume, I have some speed. So I will think about this in terms of Newton's F equals to ma, that simplifies to delta P divided by delta T. So there is a change in momentum because the air is slowing down from 33 to 0. And air also has a mass, which is going to be found by using the density and the surface area and the volume idea. Let's try to do that. So we have mv divided by t. Now, the problem is that we understand what is velocity. It is changing from 33 to 0, but we don't understand, we don't have this m by t factor. We are going to try to find this out using the idea of homogeneity. This is where we are going to keep this idea in our heads, right? So we have, to find mass, we have density is equal to mass over volume. We multiply volume with density, we find mass. So mass is equal to density multiplied by volume. Now, we don't have the volume, but we do have the density, which is 1.2. So let's replace 1.2 into the equation. Now, to find volume, we need two things. We have the surface area of the wall, which is given as 12 meters square over here, right? So I multiply the surface area, which is 12, but I don't have one more dimension. I need one more dimension to actually be able to find the volume. So here what I'm going to do, I'm going to assume that this 33 meters is being covered because of the air as it moves close to the wall in 1 second. Let's put this 1 second as it is into the equation, and we are left with 33 meters divided by 1 second. Now notice that if we look at this, this actually becomes mass divided by t, because there is 1 second factor. So this is actually becoming, let's say, mass divided by t. Some mass, density multiplied by volume, being divided by time. So this can be replaced directly into this situation, right? So what are we left with is 1.2 multiplied by 12 multiplied by 33 multiplied by the velocity change, which is from 33 meters per second to 0, right? So this velocity is already taken care of in this situation, as we've already done that. Okay, so this will become multiplied by 33 again. So divided by this 1 second, which is already a part of this equation. Again, we are thinking about units. We're not going into the formula how we make it. We're thinking about the units, that it is m divided by t. So if you solve this, you will find out 15,681 newtons as a constant answer, which is going to be 16,000 newtons up to two significant figures and on average. You can do this separately as well. You can do this part by part. It's up to you. Okay. All right. Then we encounter this question. Again, the question is not going to be a part of your course. You will not see this in books and somewhere else, but we have to be careful about this in terms of units. So it tells me that 90 kg per minute water is being pumped out at a speed of 20 meters per second. If you want to hold that pipe in a single position, how much force should be applied? Newton's third law, classic example. So if let's say we have a pipe and there is water coming out of the pipe, then most definitely there is going to be a recoil, or you can say a backward force because of that pipe or the exiting water from this side as well. So how do you find it if you don't want this pipe to move from its position? So what we're going to say is that the force of exiting water will be equal to the force experienced by the person who's holding the pipe, right? So if they both are equal, we want them to be equal so that it is prevented from moving backwards. Then both forces are equal. So if I can find the force of exiting water, I can find out the force needed by the person to hold this in place. So again, I encountered the problem with this change in momentum divided by change in time, because force is basically rate of change of momentum. The concept of F equals to ma is a bit, you can say it's very basic. The true understanding of force is change of momentum divided by time taken for that process. So it's 90 kg per minute. I can see that if I replace mass into velocity divided by t, I have the unit of kg per second or kg per minute given in this situation, right? And the velocity is 20 meters per second, already given to you. Okay, so let's carefully put in the value. So F is equal to mass is 90 kg. The velocity is already given to you 20 meters per second divided by per minute. So it will be converted into seconds. So this will be 60. Now notice that where I have put in the 90 kg per minute, I placed it here, right? Being multiplied with the velocity. So this will naturally give me an answer of force per second. It is right. So that will be, if you solve it, you'll get an answer for 30 newtons with the calculator. Okay, so this will be 30. We've already solved this question, visualizing the animation, right? This is another question in terms of the application. Let's try to see. He says, this is just a simple basic algebraic manipulation and some understanding to what those numbers would mean. What is the meaning of those numbers? So it tells me that the mass of x is m and the mass of y is 3m. They're experiencing F resultant force and they're going to experience an acceleration. So let's find out the acceleration. So F is equal to ma. So if I find F, that will be 4m into a, and the acceleration comes out as F divided by 4m. Now, if I want to find the force experienced by x and y separately, I will use Fx equals to ma and Fy is equal to ma. But be advised, they will be individual masses. So let's put in the values individually and see that the mass of x was only m and the acceleration experienced was F divided by 4m. So m cancels out. We are left with F by 4 experienced by F for Fx. For Fy, we replace mass as 3m multiplied by F divided by 4m acceleration. M cancels out. We are left with the 3F by 4. Now what's actually happening is that from this applied force, F by 4 is being utilized by X and the rest of the force is being provided to X to Y, that is 3F by 4, or 3/4 of the force is being utilized by Y to move in this direction with an acceleration A. So it asks you what is the force applied by blocks X on Y. So X is going to keep F over 4 for itself to accelerate and leave the rest of the force, which is 3F by 4, for the next block to accelerate. and that will become D. Now, we have solved them individually, but we can see that if we combine them together, we're going to get to the same answer. That in order for us to move X and Y together in a single block or as a single block, we need to apply a force of F to maintain an acceleration of A. Okay, all right. This question is from Newton's third law again. Now, since the object is accelerating, if you observe the tire, we can see that there will be a normal reaction force on both ends. So both tires experience a normal reaction force. This also experiences a normal reaction force, right? Which is of course opposite to the weight. But if it is accelerating on the forward side, we are going to zoom into the tire and see what's going to happen. So the tire is supposed to rotate in this direction, right? So that it eventually accelerates. So the tire is applying a force on the ground backwards. So this is force by tire, Ft. So what is the ground going to do, or how is the ground going to respond to the tire according to Newton's third law? You've applied an action force. Now the third law is going to respond, or the floor is going to respond as Newton's third law by applying a force in the forward direction. So this will be force by the road on the tire, right? So he's asking you about the resultant force on the wheels. So we are just going to see that very clearly that if this is the case, then the resultant force because of them will be in this direction as simply as visualizing vectors. So very clearly, this option actually comes down to option B. Okay, so this is another common example of what students generally visualize to what it actually is going to be. Okay, so now we have the concept of terminal velocity. I'm also going to show an animation for this one, and I'm going to discuss what that balanced force or unbalanced force or the terminal velocity actually goes through. One thing that we need to understand is that the drag force or the air resistance actually depends on two factors. The first one is the surface area of contact, right? So if a person is falling without the parachute, they have less surface area, their drag will be low. And if a person is falling with a parachute, then the surface area is greater, the drag will be higher. That is why parachutes are used to safely land. And the other idea is basically speed. So if an object is moving at a higher speed, it will be experiencing more drag because the air molecules or their inertia is trying to stop you from going through them as fast as you want to go, right? So the more you try to push back on the air molecules so that they can let you through them, the more force the air molecules are going to apply back on you so that you don't do that, or you're unable to do that, or you're unsuccessful in doing that. But since air is a fluid, it has no option other than to leave its position to let you through. Okay, but in the process, it will still be applying a force back on you. So if you try to go through the air at a higher speed, the air will apply a greater drag force. You can experience this in daily life. If you are, let's say, just walking by, you will feel, let's say, a moderate amount of air going through your body. But if you start running, you will feel the air to be quite high. The speed of air will be high. What has happened is that if you increase your speed, you're increasing the force applied on the air molecule, and the air molecule will start applying a greater force on you, according to Newton's third law. So let's observe this in terms of a freely falling object, right? And discuss that further. So we have a scenario in this. I'm going to explain you briefly what's going to happen so that we can visualize it clearly. At the very beginning of the motion, the air resistance is mentioned as 0, and there is only weight of the object, right? But as it achieves the terminal velocity, you will notice that the downward force and the upward force would eventually become equal. Now notice that the air resistance at the very beginning of the motion is 0 because the object is not moving, the speed is 0, the drag will be 0. As the object starts gaining speed relatively, since its speed is increasing, the drag will also increase and it will become equal to the weight of the object. When that happens, we call that stage to be terminal velocity. And that will again be a case of first law when all the acting forces are balanced. In this first half, we observe the second law when all the forces are not balanced and it observes an acceleration. At this point, you will see that the object will open parachute. And when he opens the parachute, the surface area suddenly increases. When the sudden increase of surface area is observed, the drag will increase, the drag force will increase, which means that now it will start decelerating because the pulling force is less and the stopping force is higher. So you will see a decrease in speed, eventually settling down at a lower speed with the same situation, with the same circumstance as before, but with a greater surface area, right? Let's see this animation. Let's see how it goes actually. Okay, so let's play this out. You can see that in the initial situation, the drag is increasing, right? Very quickly, the drag increases from 0 to 1.3, then keeps increasing to 3.3, then increases to 7.2, then increases to 9.8, and then eventually becomes very equal, 100% equal to the weight. And notice that at from time 15 seconds up to the time of 20 seconds and up to 30 seconds, the forces are not changing. Right now, the object is falling at a terminal velocity. The pulling force and the stopping force are equal. Now notice the object is still moving. It is still falling through air. Even if the forces are equal, it does not mean that object has to stop moving. It's not going to stop midair. It's going to keep moving. Now notice that at point 30 seconds, just about at this point, the drag force increases to 21.4 because the parachute has been opened and the drag force will be higher. It will be greater. Now, for that time being, the drag force is greater. Now, notice that the speed of the object starts decreasing. It was 40 at this point. Let me show you. At this point, it was 40, but now it has decreased to approximately 22 meters per second. Now, as the speed is decreasing, the drag will also start decreasing. It's like a chain reaction. The first factor decreases the second one decreases the first one. So if you start moving at a lower speed, we know that the speed is dependent or drag is dependent on speed. If you start increasing the drag, the speed will start decreasing, right? And the reduced speed will cause the other thing to reduce as well. Okay, so let's clear this out and let this animation run for a while. Again, notice that this will happen until both forces become equal again. They become equal but at a much lower speed. Okay, so this is how we observe a free falling object through air. Okay. So let's draw an acceleration time graph for this situation. Although acceleration time graphs are not a part of your course, but I've seen one question regarding this. So this is meters per second square. What happens during the free fall? It starts at value of 9.81 at the very beginning of motion when there is no air resistance. And since the drag is increasing, the resultant is decreasing and it eventually becomes zero at terminal velocity. Because that would be weight minus drag equals to ma. We know that weight does not change. The drag increases because of speed. Mass is not changing, so the acceleration starts decreasing. So this is what the graph looks like. It eventually becomes zero at the time of terminal velocity.